Good day everyone. I am here in front of you to discuss about Phasor. By the way, pwede mo makakopy sa akong ikuan pag-request lang mo ipa-post kung ganahan mo i-post. So, Phasor is a complex number that represents the magnitude and phase of a sinusoidal voltage or current. It was first introduced by Charles Steinmetz in 1893. Kani Steinmetz katong sa advanced math nato nga polar form sa complex number. Then the origin of the word phasor is from the word phase plus vector in 1940s from phase on the pattern of vector. And here phasor is presented in three ways. It's either rectangular form, polar form, and exponential form. Natakol na ni nato sa atong advanced math, so di lang kay ko mo discuss ani kay parihar gyapon gi-discuss ng sir, so mao na to siya. So kaning graph kay gitawag ni nato kaning argan diagram where kaning y axis sa Cartesian kay may gitawag og imaginary axis diri o kaning horizontal may real axis. So kaning line kay mao ni atong phasor z. Then ang z na siya value ya ha. So ang phi diri mao ni siya kaning angle o ang value sa r kay ang kaning hypotenuse ani. And now to transform the rectangular form to polar form, we use the identity r is equals to x squared plus y squared. So rectangular form kay mao ni z equals x plus jy. Mao to gi-discuss naman sad ni sa advanced math, so di lang kay nato itakol. So mani phi cos arctan y over x. Then from polar to rectangular, x is equals to r cosine phi and y is equals to r sine phi. So z is equals to x plus jy. So x is equals to r cosine phi, so substitute, and plus j, and y is equals to r sine phi. So factor r. So r is equals to cosine phi plus j sine phi, and this is a trigonometric form. So take note of this identity. Cosine phi plus j sine phi is equals to e to the power of j phi. So to substitute this, we can say that z is equals to r e j phi, and this is the exponential form. And here we go now to Phasor Algebra. Phasor Algebra, nagyapon ni sa atong advanced math sa. So, addition of two phasors z1 plus z2 is equals to the x of z1 plus x of z2 plus j quantity y of z1 and plus y of z2. So, subtraction, the same with addition. Their operation varies. z1 minus z2 is equals to x1 minus x2 plus j quantity y1 minus y2 close quantity. Then in multiplication, it's bit we use the polar form or Steinmetz form of complex number. z1 times z2 is equals to r1 times r2 angle quantity phi1 plus phi2. Then in division, z1 divided by z2 is equals to r1 divided by r2 angle quantity p1 minus p2. Then in the inverse of the complex number, 1 over z is equals to 1 over r angle negative phi. The square root of z is equals to square root of r angle phi over 2. Then their complex conjugate z is equals to x minus jy is equals to the polar form of r angle negative phi and exponential form r e negative j phi. So take note of these identities. 1 over j is equals to negative j. E j phi is equals to cosine phi plus j sin phi. J squared is equals to negative 1, and cosine phi is the real part of a to the power of j phi. Sin phi is the imaginary part of e to the power of j phi. To discuss further, take a look at this graph. So at this point here, Vt is equals to V max cosine omega t. So when the point reaches here, V of t is equals to V max cosine quantity omega t plus phi. Phi here is the angle when the point moves counterclockwise, the phase leads while the opposite it lags. So take this equation, V of t is equals to V max cosine omega t plus phi. So take the real part of the cosine. V of t is equals to V max real part of e to the power of j quantity w omega t plus phi. So j omega t is separated from j phi. Now, to get the real part of this equation, we copy v of t is equals to the real part of v e to the power of j omega t. This v here represents v equals to v max times e to the power of j phi. So this equation shows the time domain representation of this phasor, while this equation can be written into polar form. So let's tackle the differences between the time domain and phasor domain representation. So in time domain, it tells you the voltage as the function of time, the vector projected on the real axis at t. In phasor domain representation, it tells the magnitude and the phase angle. Here is the magnitude and the phase angle. Vm as a magnitude, phi as a phase angle. So here are some formulas that to be transformed from time domain to phasor domain. So V of t is equals to Vm cosine quantity omega t plus phi is equals to V equals V max angle phi in phasor domain. Then I of t is equals to I max cosine quantity omega t plus phi is I equals I max angle phi in phasor domain. V of t is equals to Vm sine quantity omega t plus phi. First, we transform this equation to cosine. So take note that when transforming time domain to phasor domain, you must use the cosine. So this angle minus 90 degrees. So copy that Vm cosine quantity omega t plus phi minus 90 degrees. So to write it into phasor domain, V is equals to V max angle quantity phi minus 90 degrees. So next is I of t is equals to I max sine quantity omega t plus phi. So uh, transform it into cosine, so minus 90 degrees. So I max cosine of omega t plus phi minus 90 degrees. So to write into phasor domain, I is equals to I max angle of phi minus 90 degrees. I have an example here. The equation I equals 42 sine of 628t minus 30 degrees. So to write it in phasor domain, I is equals to I max angle phi. Since it is sine, we convert it into cosine, so minus 90 degrees. So I is equals to 42 cosine of 620t minus 120. So writing in phasor domain, I is equals to 42 angle negative 120 degrees. So let's draw the phasor diagram of this equation. So negative 120 degrees. So we say that 120 degrees is here. So this angle is 120 degree, negative 120 degrees, since it's in clockwise direction, and its magnitude is 42. So that's it.
Hey friends, welcome to the YouTube channel all about electronics. So in this video we will learn about the phasors and the phasor diagram. So in a very simple way, if I say this phasor is nothing but a simple way of representing this sinusoidal signal. So now when we have more than one such sinusoidal signals which is having a same frequency but different phase and different amplitude, then we can use this phasor diagram to represent the phase difference between these sinusoidal signals. So now we know that any sinusoidal signal in a general form can be expressed by this expression, that is Vm into sine omega t plus 5, where Vm is the peak amplitude of this sinusoidal signal, omega represents the angular frequency, and the 5 represents the initial phase of this sinusoidal signal. So now let us represent this sinusoidal signal using this phasor. So now this phasor is nothing but a vector which rotates around its origin at a constant speed of omega radian per second in a anti-clockwise direction, and here the length of this vector represents the maximum amplitude of this sinusoidal signal, and its angular velocity represents the angular frequency of this sinusoidal signal. So now if we take the projection of this rotating vector on the y-axis, then we will get the instantaneous value of this sinusoidal signal. So now as you can see here, as the vector rotates in an anti-clockwise direction at a speed of omega radian per second, and if we take the projection of this vector on the y-axis, then we will get the instantaneous value of this sinusoidal signal. And if you plot all the values which is possible for this phasor, then we can reproduce this sinusoidal signal. So now let us see how we can represent this phasor on a phasor diagram. So now on this phasor diagram, different AC sinusoidal signals which is having a same frequency but different amplitude and different phase are represented. So while representing these phasors on this phasor diagram, we only represent them by their amplitude and the initial phase. So let us say we have two sinusoidal signals. The first is, let's say 5 sine omega t plus 30 degree, and the second signal is V2 is equal to 10 sine omega t plus 80 degree, and we want to represent these two signals in terms of the phasors in a phasor diagram. So the first signal is 5 sine omega t plus 30. So first we will draw the vector which is having a amplitude of 5, and it will make a angle of 30 degree with the horizontal axis or a reference axis. Now if you see the second signal, that is a 10 sine omega t plus 80 degree. So here the peak amplitude of this signal is 10. So we will draw a vector which is having a magnitude of 10, and it will make a angle of 80 degree with the horizontal axis. Now sometimes this phasor is also represented by the RMS value of the sinusoidal signal. The reason is that the most of the measurement which is being carried out by the ammeter and the voltmeter are in terms of the RMS values. So sometimes you will find that these phasors are represented by the RMS values instead of the peak value. But in this video, we will consider the peak values of these sinusoidal signals. So now let us see one more example based on this phasor diagram representation. So let us say now we have a voltage that is equal to 10 sine omega t minus 30 degree, and the second voltage or second signal is 5 sine omega t minus 120 degree, and we want to represent those signals on this phasor diagram. So the first signal is 10 sine omega t minus 30 degree. So we will draw a vector which is having a amplitude of 10, and it will make a angle of minus 30 degree with the horizontal axis. Now second, we will draw the second signal which is having a amplitude of 5, and it will make a angle of 120 degree with this horizontal axis. So we can draw a vector of a 5 amplitude and having a phase shift of 120 degree. So this will be the representation of V2, and this will be the representation of V1. Now on this phasor diagram, this anti-clockwise direction is known as the leading direction, and this clockwise direction is known as the lagging direction. So as you can see here, this V1 is leading the V2 by 120 minus 30, that is by 90 degree. So here this V1 signal is leading the V2 by a 90 degree. Similarly, in the first case, if you see, this V2 signal is leading the V1 signal by 80 minus 30, that is by 50 degree. So now so far we have seen that how to represent the phasor on a phasor diagram. Now let us see how we can represent this phasor in a mathematical form. So the first form is the polar form, where we can represent this phasor in terms of r and theta. So suppose we have a phasor which is having an amplitude of Vm, and it makes a angle of phi with the horizontal axis. Then in the polar form we can represent it as Vm and phi. So the next form is the rectangular form. So in this form we can represent any phasor by a complex number, that is a plus jb. So the amplitude of this phasor will be under root a square plus b square, and the phase of this phasor can be given by the expression tan inverse b by a. So this will be the rectangular form of representation of this phasor. Now the third form of representation is the exponential form, where we can represent the phasor in terms of Vm into e to the power of j5. So these are the basic three representations by which we can represent this phasor.
Thank you for listening, and God bless you all.